teaching that I've remembered all the things I need to do. Like my camera's on, my screen is being shared, transcription is on, and the recording is on. This could be the first class that I'm fully prepared for. Hello, everybody.
That's good.
Yeah, I'm impressed to see that I've got all my stuff together. All the tutors are here and ready to go. We've got a pretty full group of students ready to learn. It's only downhill from here. This is going to be the peak QDA week 3 and then down. But hi, welcome everybody. Glad to see so many people already here, and I'll talk slowly as I start things off so people have a minute to get in. You know, you might be coming from another class or getting to the library or something like that. This is week 3 to QDA, and I just wanted to remind everyone to feel free to put comments and questions in the chat, or even turn on your mic and ask them out loud as we go. Paula and Yunhan will be in the chat to answer questions as we go, and I'm sure I'll be distracted as usual by anything that pops into chat, and I'll answer right away. Today's lecture will be about graphs, about visualizing your data, and about variance, the amount of spread in your data. So last week we talked about measures of central tendency, and this week we're talking about the extent to which your data deviates from that central tendency. These two descriptions, center and spread, really tell most of the story about your data, and those two things will underlie pretty much all of the statistical tests we cover in this module. So if you were getting all excited that finally it's been 2 weeks already, we're on to week 3, I finally get to learn a statistical test. Well, I have bad news for you. That starts next week. We do have to get a basis in variance and in central tendency before we can do any other kind of testing. But after this week, each lecture will be about a specific statistical test. And we also wanted to quickly remind you just to make sure you're being proactive about reaching out to each other or to us if you're having any difficulties, either with statistical concepts or with coding throughout the module. We know each part of that is tough to learn, so learning both at the same time is really tricky. And remember to make use of the buddy groups on Brightspace and make use of our office hours as needed. No sense falling behind early on and digging yourself into a hole, because inevitably you'll get more work in all of your modules as the term goes on. That hole gets bigger and bigger. We definitely find with this class, asking questions early can really help you get out of that hole early. Normally the things that aren't clicking early on, if you can get them resolved, they're normally pretty easy to get resolved early on, and they make everything else fall into place a lot more. The hope is that over time, this module gets easier and easier instead of harder and harder, but that only happens if you're proactively seeking the help and information you need. Anyway, with all of that out of the way, why don't we get started with our first graph of the day? And our first graph will be a histogram. In this class, every time we get a new data set, it's always good to visualize that data set. There's a few pieces of code that I pretty much always run when I get a new data set. So I showed you a couple of them last week, the head and tail, but I also run things like a histogram. A histogram lets us see how the values in a column of data are distributed. So how frequently did each different value occur? So let's imagine a data set. I didn't save this data set anywhere, so it's not one we're going to be doing further analysis on. But maybe we get data for some experiment on how many minutes per week people spend using a particular app. And for the purpose of today's lecture, let's say that app is Spotify. So we could find the average or some other central tendency to help us describe that data. But that central tendency only tells us one part of the story, that maybe we have an average of 250 minutes per week of using Spotify, but that could be because everyone's using the app for just about 250 minutes, or maybe it's spread out. Maybe there's a bunch of people who use it for 100 minutes and a bunch of people that use it for 400 minutes. A histogram helps us get a sense of that distribution by visualizing how many times each different value occurred. So for this data, you can see that we had about 800 participants that used Spotify between 240 and 260 minutes a week. So I say 240 to 260 because you can see between each set of 100, there's 1, 2, 3, 4, 5 bars. So this third bar, this first one's 200 to 220, this one's 220 to 240, This one's the 240 to 260. And I say that it has about 800 people that used it that much because this bar goes up to a height of 800. That's pretty much all the histogram's telling you. It's telling you which values occurred and how often each value occurred. So you might also notice that for this histogram, we have for people in the range of 200 to 220, that's maybe about 600 people. And maybe that's about the same range in the 280 to 300 bar. So these are both around 600, I would say. That means that 600 participants use Spotify for 200 to 220 minutes a week. And another 600 used it for 280 to 300 minutes a week. So what are we looking for when we have a distribution like this? Why even bother looking at a histogram? Well, the first thing we can look for is if there's any bad data, like if there's any participant that we had written down as like negative 200 minutes or as like 2 million minutes or something like that, we would see one bar way off on its own on the histogram. Luckily, with this data set, I didn't have any bad data, so that's not a problem. We can see that our range is from about 50 minutes a week of use to maybe about 420 to 440 minutes a week of use. That seems perfectly plausible. Those are neither of those are so crazy that we think it's like definitely a data error. So that's the first thing we're checking for. But the second thing we're checking for is if our data looks normal. That is to say that it follows the bell curve that looks like this. I just drew this bell curve myself. There's nothing magical about the way I drew it. But a normally distributed data set or a Gaussian distribution, you might hear it called, is one that follows this pattern where most of your values come from the middle, and then on each side, it kind of decreases by roughly the same amount. Normal distributions are what we expect to see with any variable that has a finite mean and variance that we took random samples from. So if we took a random sample of people who use Spotify, we would see a bell curve of results. It's not a parabola because a parabola does not curve in at the end, right? A parabola continues down, it's a straight line. A bell curve is a different shape. So the significance of the bell curve, as I said, it's the idea of a normal distribution. So if you have a variable that's random, that has a true mean, that has some true standard deviation, and then is randomly sampled from, so you're just taking random people and getting their value for that variable, then that random sampling should always produce a distribution like this. You can read more about it in the textbook, though. Andy Field goes into a bit more detail about what is meant by a random variable in that way and what is meant by random sampling. But in this case, we see that nice normal distribution, that nice bell curve. And the reason we're looking for it, the reason we want to find it, is because all of the statistical tests that we get into for all of the future classes we'll cover assume that your data has this normal distribution, that the test only works on normally distributed data. Right now, we won't worry so much about what to do if you don't find that bell curve. We'll have some more options that we talk about later on, and also that the book gets into. But for the most part, what you want to see when you get a data set is this normal distribution for whatever your variables of interest are. For now and for the next few weeks, we'll just use the eyeball method to check if our data is normally distributed. So we'll look at this histogram and say either, yeah, it looks normal enough, or we'll say that's definitely not normally distributed. But in a few weeks, we'll also introduce a more foolproof method to test if we truly have a normal distribution. But for now, the best way to check if you have normally distributed data is to just make a histogram and see if it roughly follows that bell shape. Yeah, someone asked, is it possible for this class to be hybrid on Zoom and in class? You can all get together somewhere, but I will not be there, and I'm the one teaching it. So the access to me will always be remote, but the access to each other is purely up to yourselves. So along with a visual pattern of the distribution, it's good to check out what the dispersion of the distribution is. So not only how wide is the curve, like what were your absolute ends, but also how tall or how flat was the curve, because you could have the same kind of starting and ending point, but all of the values with the same amount of frequency, or you could have like way more people right at the median. So these are the questions that dispersion of distribution, these are the questions about dispersion of distribution that you can start to answer with a couple of ranges. First is just your plain old range, absolute range. You take the biggest number, you subtract the smallest number, and you get the range. You know how wide that histogram is, how wide the distribution is. For our Spotify example, it's how many minutes of listening per week did our participant that listened the most listen to, and how many did the person that listened the least listen to, and then you just subtract them. So for us in the last example, it was something like maybe 440 minutes minus about 40 minutes. So our range was somewhere around 400 minutes. This is yet another way we can see an extreme score, that if someone listened to like 5,000 minutes per week, but we had a median at 250, we would know that there's this one really extreme value because our range is so much bigger than our median. If we know the range of our data is 0 to 200, is it okay to clean minus 100 before making a histogram? I'm not sure what you're asking. I would like to have a more clear description of what you're asking, but I would say no, you should always you should make your histogram of your full data set or of whatever version of the data you're running a statistical test on, because you're looking to see if what you're running the test on is normally distributed. So you can't remove data points ahead of time. Is that how YouTube algorithms work? I'm not sure what I'm not sure what you're asking with that either. Hopefully the chat will populate with more specific questions because I feel like I'm getting confused right now. Anyway, that's what your absolute range is, just your max score minus your min score. Your other measure of dispersion that I introduced last week, but I kind of introduced in a rush and I didn't do a great job of, is our idea of interquartile range. So I put a visualization of what that means this week. But for any set of numbers, we can find our median, our middle number, our 50th percentile. That's the number that separates our data into an upper half and a lower half. And from there, we can also get medians of each half. The median of our upper half is known as our 75th percentile. That's the number that's bigger than 75% of our data. And the number that's the middle of our lower half, the median of our lower half, is the 25th percentile. That's the value that's bigger than only 25% of our data. Rather than talking about a range of absolute max minus absolute min, we can actually talk instead about the range of data between those quartiles. We know that 25% of our values are below that range, 25% are above that range. So exactly half of our data falls inside of that range. For this little example in the picture, you see the median is 54. You know, it's somewhere between 53 and 55. You just split the difference and you say 54. And you find that the 75th percentile is 58. The 25th percentile is 52. That means we know that the interquartile range is 6. You just subtract those numbers and you know your interquartile range. That is to say that 50% of our data is within a range of 6 values, so just between 52 and 58 with a median of 54. So we know everything's pretty tightly packed, or at least the middle is pretty tightly packed around that median. By excluding half of our data, specifically the most extreme half at the top and the bottom, we get a measure of dispersion that isn't influenced by extreme scores. That way, we not only have an idea of our total dispersion, but we have an idea of how dispersed the middle is. Is it kind of flat or is it really tall? This is our indication, of how tall or how flat the bell curve is. And this is important for the next visualization we're going to get into, the box plot or the box and whisker plot. So you don't necessarily need to report an interquartile range when you're reporting descriptive statistics. It's not terrible to report one, but it's not absolutely necessary to report one. It's more just, I like teaching it and talking about it more so we get an idea of how that dispersion is being measured in the next visualization that we use. Because the next thing is another one that anytime I get a new data set, it's like the first, one of the first things I do to each variable of interest. That is to make a box and whisker plot or a box plot. It's useful to know about IQR because this is a vital component of the box plot. Box plots are a visualization that we should do to any new data set because they give us a lot of information. They let us see the dispersion of the distribution just like a histogram, but instead of telling us how many values we had at each point, the box plot only tells us how far away values were from each other. It's kind of like if our histogram is like a 3D object, and instead of looking at it from the front where you can see the heights, like instead of looking at the mountains from standing on the ground, you're looking at it from over top. It's like flying a drone over the mountains. So you can't really tell how tall they are, but you get a better idea of how wide they are without any influence of that height. This is how we get to see what the dispersion is like. This lets us see if the data is symmetrical, whether it's bell-shaped on both sides or if it's skewed to one side or the other. If there's more extreme values on one side of the median than there are on the other. It also lets us get an idea if there might be outliers. Outliers are extreme values that are much different than the rest of our data. They might represent data errors, something that was recorded incorrectly, or more often, they might represent special cases, like the one strange person in our data set who listens to Spotify for 20 hours of the day every day. For some of our finding trends, it might be good to exclude or to replace certain outliers because they might be masking a trend that the rest of the data could be represented by. But in general, it's also good to investigate those outliers that maybe if you're doing a mixed method study, if you're not only seeing how many hours people use Spotify, but you're also interviewing some of your subjects, you might decide to interview that special case because now you know it's a special case. I'll show you a box plot now, but I of course wanted to show a cat because it's called a box and whisker plot, and there's a box and there's some whiskers. This is not my cat. My cat looks pretty similar. She's actually on the next slide. Oh, there she is. She hasn't joined for any lectures yet, which is weird, but hopefully she will soon. Here is a labeled box plot, but first I wanted to just take a peek at the chat. Yeah, it looks like the tutors are all over this. All right, yeah, okay, fine. I'll go back to the cat while we wait. Paola's right to say that machine learning algorithms are based on statistical models, but we're not quite to the point that we're doing machine learning yet, for sure. But in general, the idea of fitting a model to data is what any of these machine learning algorithms do. So this is the basis of machine learning and of a lot of AI. So nice, got some free hearts and +1s on my cat picture. I knew that would be a good inclusion this week. I don't have a TikTok sound, unfortunately. Here's a labeled version of a box plot. So when you draw a box plot, or when R or whatever other statistical program you're using draws a box plot for you, it draws a box with lines at the upper quartile and the lower quartile, and one more line right at the median. It uses those lines to make a box. That's the term box plot. It then draws the whiskers, those horizontal lines, out 1.5 times bigger than the IQR away from each of the quartiles. So this maximum here is Q3 plus 1.5 interquartile ranges away from there. And then this one is 1.5 interquartile ranges lower than the first quartile. It then might also draw some dots for any data points that fall outside of those whiskers. These are what a box plot would consider an outlier, but we have better statistical ways to detect outliers. So in general, the box plot's more giving you a hint about where outliers might be, but it does not get the final say. Skewed is where the data shifted left or right. So I'm going to show you what a normally distributed box plot looks like. Then I'll show you a skewed box plot in histogram. So when you make a box plot in R, here's what a data set similar to the Spotify example would look like. Admittedly, I made random data for the first histogram, and then I forgot to save that random data. So I couldn't make a box plot for the same exact data. So I made a very similar but slightly different data set represented by this box plot. But it's the same idea where your median is somewhere around 250. Your max is somewhere around, maybe in this case, it looked like more around 350 or close to 400. The minimum was just below 150, and it looks like there is an outlier here below 1 point below what the box plot would call the minimum. So we had one lower outlier down there, but again, that's just a hint. We'll later on next week and in the future talk about what to do with outliers and how we actually check if this counts as an outlier. But this is the box plot telling us you might want to look at this data point. The two things that I'm really interested in, though, are how long the whiskers are in comparison to each other and how long the box is as compared to the median. So to me, this looks like a really symmetrical box plot. This looks like a normally distributed data set because this box is really symmetrical. The median falls right in the middle of it. Also, the whiskers are really symmetrical. It's not like we have one really long one and one really short one. That can happen if you have non-normally distributed data, if you have skewed data. So in the next slide, this is more of a skewed data set. This is a box plot with maybe the same rough median and max, but much more of a skew. You can see that the box isn't symmetrical anymore. There's a lot more points between, or there's a lot bigger of a gap between the first quartile and the median than there is between the median and the third quartile. Likewise, there's a way longer whisker, there's a way higher max above the third quartile than there is below the first quartile. What we might expect to see is that the lower half of values in this data set are really tightly packed. They're really tightly in that 220 to 260 range without a lot going that far below the mean. But on the other side, the upper half might have some really high values above the median, but not so far away that they're considered outliers. So what would that look like in a histogram? This is the histogram that's defined by the same box plot. So like I said, we have a bunch of lower values kind of tight. If we look at this histogram, our median's actually probably here, even though there's this high bar in the middle, just because there's a high bar there too. So to get an equal amount of values, it's probably close to maybe 250, 260 area, but not above 260. So we have a lot of values tightly packed between our median and the minimum. And then we have this one like pretty extreme bucket of values up here. This could be one person, it could be a bunch of people. It really depends how much, what our frequency is. I cut off the y-axis so you don't know how I made my data sets. But this box plot goes with this histogram that it's an extreme value up here and tightly clustered data down below the median. And that's just what we see here, an extreme above the median and a lot of tightly clustered stuff below the median. So if we saw this box plot or if we saw this histogram, we could conclude that we don't have normally distributed data. Someone said, I think I've seen a whisker plot before. They used in Forex. Yeah, I think candle charts in a lot of like financial technical analysis use box plots. Yeah, so a box plot, again, I'm going to go back to the label diagram because I think this will kind of help you understand what's happening. So the first thing that happens when a box plot is drawn is you find the median, you draw a line for the median, then you also draw a line for the first quartile and the third quartile. So the two quartiles that make up the interquartile range. That's where you draw your box. Now you're putting this on an axis, you're graphing it, right? So it's not that they have to be symmetrical, they just fall where they fall. It might be that the third quartile is really close to the median and the first quartile is really far away. It completely depends on your data. In this example, it looks symmetrical because there's not an axis here, there's probably not real data underlying this. But when you draw this on an axis, like my example with R, it actually has to put that line somewhere. It has to put a third quartile right where it actually existed for my data. It has to put a first quartile where it existed for the data. That draws the box around 50% of your data. So these are the 50% closest to the median. The group that's between the 50th and 75th quartile, and the group that's between the 25th and 50th quartile. That's 50% of your data represented there. The whiskers are drawn by adding 1.5 times the interquartile range to the third quartile. So going whatever Q3 is plus 1.5 times the interquartile range, you draw a whisker up to there. And then for the other whisker, you go 1.5 times the interquartile range subtracted from the first quartile, draw a whisker there. So the interquartile range is whatever it is, it's this length. So 1.5 times that length down to here, and you draw a line, 1.5 times that length up to here, and you draw the line. And that's how you get your interquartile range. How's 1.5 times the interquartile range determined? So interquartile range is just take your top half, take your lower half, find the median for each half, and subtract medians from each other. So here you found your top half, the median was 58. You found your lower half, the median was 52. That means the interquartile range is 6. You can subtract 58 minus 52 to get 6. That's your interquartile range. IQR times 1.5, 6 times 1.5 would be 9. So if I drew a box plot with this data, I would draw a line for the median, so a line at 54, lines for each of the quartiles, so a line at 52 and 58. And then I would want to go 9 above the upper quartile, so another line at 67 and a whisker, and then 9 below the lower quartile, so another line down here at 43 and another whisker. So if this was represented by a box plot, we wouldn't have any extreme values below this whisker. Like I said, it's 9 below there, so it's 43. But above this whisker, 9 above 58 is 67. So we would have one outlier above that whisker. So if someone asks for an example where we would use this, my best example is this Spotify data. So I got my data about this, about how people are using Spotify. I have whatever amount of people telling me how many minutes per week they use Spotify. So I just draw my box plot. This is just to see why is it inverted. R draws things vertically. This was from Matplotlib library on Python, which draws box plots horizontally. Depends if you're doing your values on your X or your Y axis. As you can see, R does the values on the Y axis. I guess Python does them on the X axis, but it doesn't matter. But yeah, my real life example is this Spotify data. So how many times a week did you use, or how many minutes a week did you use Spotify? Everyone gave me how many minutes a week they use Spotify. I plot it, and now I have an idea of how dispersed my data is. So I already knew what my median was. I probably looked for that first. And now I have an idea of how spread that data is, of how tight that box is, whether it represents, whether there's a lot of values in that box, and or whether there's a big range of that box, whether it represents most of my range, like not many values fell outside of the quartiles, because of course there can be ties. You could have had a bunch of values tied as being the third quartile. But no, this looks like about 50% of my data is in the box without ties. It's a nice spread that these whiskers are of the same length, and there was only one extreme low value. So the main thing it's telling me is that I have a symmetrical data set, and that I have one extreme value, or one possible extreme value. Someone said, how can you have whiskers of different lengths? Well, you actually do have a true minimum, right? That you don't have to draw the whisker all the way to some theoretical point if the theoretical point doesn't extend beyond your minimum. So this whisker is actually probably being drawn where the minimum of the data set is, rather than where the theoretical minimum would be if I just drew it 1.5 times the IQR below. So in this case, there's a shorter whisker because the minimum doesn't even get as far as, so my actual minimum value here was like 210, that I could have drawn this whisker further if there were lower values, but I didn't have values like that. And that's what's reflected again here, that I didn't have a value below 210, but even if I had a value that was like 180, that probably would have been encompassed by this whisker. As you can see, it still had some room to go before it hit its maximum length. Yeah, so when we do a box and whisker plot and when we do a histogram, these are tools for us as data analysts just to check our data before we run statistical tests. If you read a scientific paper, if you read a quantitative paper in the field of HCI, for instance, like something that me, Paula, or Yunhan helped to write, then you would not find a picture of a histogram or a picture of a box plot, because they're not really testing your hypothesis. You don't want to give the reader all this extra information. You would say something more succinct, like we ensured that the variables of interest were normally distributed, or we visually inspected that these variables were normally distributed, or we detected an outlier and we treated it, or whatever else. But you wouldn't generally put them in a report, or for instance, in a report that you're writing for this class, hint, hint, hint. But you would probably want to see them in your code, that you do always want to visually inspect your data before you run any further statistical tests on it, even if those aren't visualizations that you're going to show anyone else. It's just important to see what your data looks like before you do any stats to it. So one final visualization I do to any new data set that I get, especially if I'm comparing two variables, if I collected data from two variables, is a scatter plot. So scatter plots can be used for just one variable, but they're a lot more useful when we have two variables, like if we have a cross-sectional study and we want to understand the relationship between two continuous variables. When I say continuous variables, I just mean variables that are either interval or ratio scale. So say, for example, with my Spotify data, I asked people not only how many minutes a week do you spend listening to Spotify, but I also asked how many minutes a week do you spend commuting. So now if I place each participant's data on a plane with axes for how much time spent commuting and an axis for how much time spent listening to Spotify, I get a visualization of how that relationship might exist between those variables across all of my participants. And here I made this data up, but here you can see that it looks like there's a pretty strong linear relationship that as commuting length or commuting time increases, so does Spotify time. Next week's lecture, we're going to talk about measuring the strength of that relationship between two variables, the idea of a correlation. But for now, we're just going to talk about scatter plots as your first step to examining whether two variables have a linear relationship at all. And when I say a linear relationship, I mean this idea that as one increases, the other increases, or as one increases, the other decreases. But you could have variables that don't have a linear relationship. So maybe if I plotted commute time against age, I would find a nonlinear relationship because I would expect that children and teenagers have very little commute time per week. Then adults, there's probably some normal distribution. There's like some kind of curve of that people maybe as they age start to gain in commute time. But then as they get older, they might choose work that's closer to home, or they might end up retiring and not having a commute at all. So we would expect really low ends for children and for older adults with some kind of shape in the middle that might rise and fall. That way we might have like a parabolic relationship rather than a linear relationship. That's what a scatter plot can help us determine, whether or not there is a linear relationship at all in which one variable constantly rises as the other either falls or rises. So this might be our hint if we were doing correlational analysis, which we'll get to next week, whether a correlation is an appropriate test or not. Notice that the variables on a scatter plot are usually cross-sectional variables, not experimental, because in our experiment, we tend to have a categorical dependent variable. So in our driving example from last week, where you were either texting and driving or you were in the control condition, that's a categorical variable. So I couldn't really plot it like this. There wouldn't be a good place there wouldn't be a good way to represent an axis using just two categories or using just a category at all, no matter how many values there are. With cross-sectional data, there's no independent variable, there's no dependent variable. That means there's no cause and effect relationship. So back to this example, the commute time and Spotify time. I could say that commute time and Spotify time are related, that they rise and fall together. But I can't say that that's evidence that commute time influences Spotify time. I can't say that as commute time increases, that causes Spotify time to increase. Something else might be influencing both, like maybe people who make a lot of money commute longer for their job and also listen to more Spotify. Or maybe there's some other variable that's influencing both. Someone said, why are they just not just dots, but small circles? Any significance? No, in R, you can change what they are. You can make them dots, you can make them circles. I like to keep them as circles, and R makes them circles by default, just to see if there's some overlap, that if there's two little dots, it might not be easy to, and they're all kind of in the same spot. It might not be easy to, at a glance, see whether there's like one dot there or a bunch of dots. Where with circles, if they're even a little bit off, you can see them overlap a little bit, and that helps you see if there's more of them there. But it's just a style thing. You can choose to make them dots or triangles or X's or circles. And R lets you choose between like all of those things. Like R doesn't force you into one shape or the other. So why do we use statistics? We use statistics as a way of modeling data, a way of representing data in a way that's easily understandable. So instead of, if you ask me, Justin, describe how much people use Spotify per week, and I had that data set, it wouldn't be very understandable if I started just reading every single person's number to you. If I started saying, well, participant 1 uses it 240 minutes a week, participant 2 uses it 320 minutes a week. That's not easily understandable. That's not useful. We want to be able to describe our data through general trends in a kind of succinct way, and not having to read every single data point. our first measures of central tendency, like mean, are our first crack at modeling a variable, at describing them in a quick way like that. So I made up a new data set here. This is just students' grades on a test. And I put a line at 78 because that was my mean. Now, if you ask me, describe how students did on this test, I could tell you that student 1 got an 80, student 2 got an 80, student 3 got maybe a 25, 20. That's not a good way to sum up the data for you. Instead, I might say that the mean for my data was a 58. I think I accidentally said a 78. The mean score was 58. Now I'm talking about a model. I'm saying that 58 describes the central tendency of the data. That's our initial model for describing the data. But as this graph title says, and this is a theme we'll get back to later on, the mean is a poor model. The mean alone isn't enough. It's okay at describing some of our data points. It looks like maybe student 6 got pretty darn close to a 58. That's not a bad way to describe their test score. But for students like 3 or student 8, the mean's a pretty terrible way at describing their data because it's just so far off from where their data point was. Yeah, I'll step back for a second. So in this example of a study, I said that Spotify and commute time were both cross-sectional variables that I asked people to fill out a survey where they told me, what's your name? What do you do for work? How many minutes a week do you listen to Spotify? How many minutes a week do you commute? And I might see this nice linear relationship. I might be able to say that they're related to one another, that as commute time increases, we also see an increase in Spotify listening time. But we can't say that there's a causal relationship in these variables because of confounds, or last week, as we said, because of Steve. There's third variables. We didn't control anything, so we can't say that one thing caused another. This is very unlikely, but it could be that people that get really into Spotify decide that they want to commute longer. That, like, let's say I'm a Spotify premium user already. My commute's not bad right now, but I'm like, you know what? I want more time to listen to Spotify. I'm going to take a job that's farther away from work. That way I can listen to more Spotify. Even though that's very unlikely, we didn't assign people to one condition or the other. We didn't tell them how much to listen to Spotify or tell them how far to commute to work. Therefore, we don't know if one thing is influencing the other or in which direction they're influencing one another. So I can't say there's a causal relationship because there's no control. My other example of a third variable here is money. It might be that people who get paid a lot are willing to commute farther, or maybe they can afford a nicer house, so they live farther away from each other, live farther away from their job. So those people have a bigger commute. And maybe also because they're rich, they buy Spotify Premium and they like using it more because there's no ads and all this. Therefore, it might be that some third variable, like income, is influencing both variables. So we can't say that one is causing the other because something might be causing both, or we might be wrong about the direction of which is causing which. Someone else asked, can you explain with these examples where it will be easy to know how and where used? Yeah, I think the best way to answer the question that I got DM'd about where and how we apply some of these is actually in the practicals. So in each week when we get a data set, we'll go through what we would actually do with that data set, depending on what our hypothesis might be. And we can't really test hypotheses yet because next week's class will be the first one where we get a statistical test. We'll start talking about correlational tests, which can test a hypothesis. But for now, it's more just examining the data set, checking it out, right? Looking at a visualization of what the data looks like to describe it, to use these descriptive statistics like median, mean, and the descriptive statistics I'm going to get to in a moment about dispersion called standard deviation and variance. But for now, leave it for the practical. And if you're still not sure when to apply these things after maybe this practical and next week's, then we can talk more about when is appropriate. But for now, I'm giving you all the tools because I want you to use all of them all the time right now. So scatter plots, histograms, box plots, pretty much any data set you get, any variable you get, you should throw these at them just to look at them. And that's also the beauty of R, right? That if you run a certain test or if you do certain visualizations of data, Even if it ends up being the wrong thing, you don't have to tell anyone you did it, right? You don't have to tell me that I looked at a box plot even though I didn't need to. You're the data analyst. Look at the box plot if you think it might give you information, and if there's no information for you to get from it, don't bother looking at it. But it's fine if you get information you didn't need. That's kind of the beauty of these descriptive statistics and visualizations, that they don't hurt to look at. So as I said, the mean is a poor model that we want to not only represent what our central tendency was, but we want to represent how far individual data points were from that central tendency. The extent to which data points differ from our model, this distance between the actual value and the mean, is that point's deviation, or sometimes known as that point's error, or that point's residual. These come from like a long bygone era of statistics where instead of just calling it differences, we're calling it error, deviation. It makes it sound bad to not be the mean. But nonetheless, it's important to capture not only what our central tendency was, but how much our data on average differed from that central tendency. These arrows help us see each point's deviation, how far each individual data point was away from the mean. This collection of deviations helps us get towards statistics, which describe how much deviation there is overall. The first of those statistics is variance. So notice that some of these arrows are pointing up, others are pointing down. So some points are higher than the mean, some points are lower than the mean. That is to say, some have a positive deviation, some have a negative deviation. We want to get a summary of all this deviation, but if we just added up all of those numbers, we would have positives and negatives canceling out, and we might not get a very good idea of the total distance. We might say there was zero deviation because like all of the positives and all of the negatives canceled out. But clearly looking at this graph, there's not zero deviation. There's some deviation there. So instead of just adding them all up, the first thing we do is square them. So instead of just adding up positives and negatives, if you square all of those numbers, that means all of the negatives become positives, and then you can add them. So in order to calculate our variance and not worry about negatives, we just take each point's deviation, we square that distance, and then we get a bunch of positive numbers that we can sum together. This sum is called the sum of squared errors. You don't necessarily need to know that. That's just, the more you know. So the distance from our mean is the error. We square it and get all these positive numbers, sum them all together. We get our sum of squared errors, sum of squares. Now we want to use this data, this sum to get an average so we can describe each individual data point. That we don't really care how much total deviance there was, because if we had lots and lots of data points, we might expect more and more deviance if we're just adding them together. So we also need to divide them by our number of participants. Specifically, we divide by our number of participants minus 1. This is a concept we'll talk about in the future called degrees of freedom. But the general idea is like we need one person's data to like stay in place so we know what the mean even is. That since we're using the overall mean and describing it here, we can't subtract by every single participant. They weren't all free to vary. That's a little confusing. I'll talk about it later. But just know for now that when we do the average in variance, we don't divide by the total number of participants or the total number of data points. We divide by number of data points minus 1. Keep that point constant, let everyone else free to vary. That gives us our variance, our mean squared error for the population. So variance is sometimes abbreviated as S squared because we did that squaring step. Now, it's not that useful to have variance because it's in squared units. So we would be describing our variance by saying that the average distance from the mean in our test grade data set was 100 grade points squared, or with our Spotify data, our average variance was 2,500 minutes squared. That's weird to talk about, right? We've squared the numbers, so we've also squared the units, and now it's not a very sensible unit to talk about, but it's a pretty easy solution. If we want to talk about the units in the original unit, we can just take the square root of our variance, and that gives us a standard deviation. So now we can express the dispersion of our data, how far each point was on average from the mean, with a single statistic in the same unit as the data itself. So we can say that students had a mean grade of 58 and a standard deviation of 10. And we know that that 10 is 10 points on the same scale as that mean, the 58 points. So we know that the average student was somewhere within 10 points plus or minus of 58. Or that our Spotify listeners had a mean of, let's say, 250 minutes listened per week and a standard deviation of 50 minutes per week. So that tells us that in general, we can expect that any given participant was within about 50 minutes higher or lower than 250 minutes listened per week. Now we're describing the dispersion in a way that describes a lot more of our data, but it does it all in one number. This lets us know on average whether our data were really close to the mean, whether everyone was really packed in tight to the mean, or if it was more spread out, if the mean was a pretty bad model overall because everyone was far away from the mean. So now with just two numbers, just mean and standard deviation, we can express not just the central tendency of the data, but how good or bad of a model that is, how far each data point was on average from that central tendency. This tells us a lot about the data in just two statistics. Mean and standard deviation, for that reason, are two descriptive statistics that you should pretty much always report for any variable you're studying, along with the number of data points you had. So you might say, we collected the amount of time people listen to Spotify, n equals 500. We collected data from 500 people. The mean was 250 minutes per week. The standard deviation was 50 minutes per week. So those two pieces of descriptive statistics should pretty much go in any description of any data that you're doing. They're really useful because they tell us so much in just two data points. Now, it's important to think about why we are doing statistical tests in the first place. Why bother describing data? Why are we collecting stats and doing analysis? In the case of our Spotify example, if I surveyed 500 Spotify users, that's not super interesting to just tell you what's going on with them. It's more interesting if I'm trying to tell you about what people who use Spotify in general everywhere are doing. But I probably can't get data from every Spotify user on Earth unless maybe I work for Spotify. But even then, I might not be able to get data from everyone just because there's different data privacy laws in different countries. I might not be able to combine all of their data in some grand way. So in general, I can't get the data from my entire population. I can't do statistics about my entire population. Instead, I'm doing statistics on a sample, on a small part of that population, to talk about the broader population. Likewise, with last week's example of the car study of the measuring if drivers who are texting react slower than drivers who are not texting, I could not possibly bring every driver on Earth into my lab and make them do this study. But I get a sample of the population so I can make some claim, some estimate about the trend at the population level. I can't be super precise. I can't say for sure that this is the exact reaction time people have overall in the world, but I can use my statistics about my sample to make an estimate about the population. And how do I do that? Well, I have a couple of pictures from the textbook. Hopefully you've seen the textbook before, but if not, this is what it looks like. This is Andy Field's drawing of a population and a sample. So this is a bunch of samples from the wider population. This is the idea that maybe your overall population, that Greek letter mu means mean. So the mean happiness on a scale of 1 to 5 for your overall population is a 3. Now, if you get a bunch of samples, they're all going to have different sample means. That this sample here had a mean of 2, this sample had a mean of 5, this had a mean of 1. So they're not exactly the same as the population mean. You have a distribution of sample means, but taken together, these samples let us know what the population is. If we had every single possible sample, then it wouldn't be hard to get the total population mean because they all add up to be the population. So they let us take a better guess. So collecting data about one sample lets us take a better guess at the data about the population, because we know about distributions of population. So this is these two diagrams go together in the book. You can see the bottom of the arrow pointing down, and then the top of the arrow, the bottom of the arrow. By combining all of these sample means, we would get a distribution of the population. And we know statistically that that would create this normal distribution, this bell curve. A histogram of that same sample would look like this. So these are the means, plotting the means of each sample. So we had one sample with a 1, we had a few samples with 3s, we had one sample with a 5. this is the histogram of those means. And we know that, and this is just something we know statistically. Andy Field gets into the math of it, but I'll spare you because I don't think it would fit neatly into a slide. We know that the distribution of sample means follows this normal distribution. We, of course, won't get every sample. We won't know where our sample is on this distribution, but we'll know for sure that it is somewhere on this distribution. We might have gotten for our data set, no matter what variable we're measuring, we might be here on the distribution, we might be here, we might be there, but we know our mean is somewhere on that distribution. And that is how, that's very important to know, because that lets us make estimates, make predictions about the entire population. How far might we be from the population mean? It sounds unknowable. It sounds like we couldn't even possibly predict how far our sample's mean was from the entire population's mean, because we could be anywhere on that distribution. But luckily, it's not unknowable. It's actually statistically calculable. This distance of how far our sample's mean was from the actual population mean is known as standard error. And we can actually use the standard deviation to estimate the standard error. So we know, if we know the standard error, we know how good of an estimate our mean is for the mean of the whole population. We can use our standard deviation to estimate the standard error. So we can say that our mean is, with some confidence, on this distribution. We don't know where on the distribution it is. We know our mean might be here. We know our mean might be here. But because we know it's on that distribution at all, and we know the standard error, we know the distance of that distribution, we can place ourselves, we can put down an interval of where that possible population mean is based on our sample mean. And that's the idea of confidence intervals. Now, this is a third thing you will learn from Andy Field's book. He likes using body examples. He likes using risque examples. So this is an example of, I think, sperm samples from some sparrow species or something. I don't know. I don't pick his examples for him, but this is his illustration of confidence intervals, that here he plots his sample mean as a dot, and then he can draw these whiskers out to express that my mean is somewhere on the distribution of the population mean. The actual population mean could be as low as 2, could be as high as 16 based on my sample. Then based on his other sample, his mean was here. The actual population mean could be as low as 4, could be as high as 15. But just from our sample mean and our sample standard deviation, we have some guess about where the actual mean for the entire population is. We get to estimate the population from the entire, we get to estimate the mean from the entire population, in part because we know the shape of a normal distribution. We know that in a normal distribution, 95% of values fall within 2 standard deviations of the mean, and 99% of values fall within 3 standard deviations of the mean. So we can express a 95% confidence interval or a 99% confidence interval by drawing these whiskers 2 or 3 standard errors away from our sample mean. And that's really powerful stuff. We took a sample that's much smaller than the population, but now we're making a claim about the entire population. We're not making a specific claim. We're not saying that the mean for the population is this one number that I found. We're saying it's somewhere in this range, but still we're getting to make a claim about this much broader population that we only sampled part of. This in general is the power of statistics, collecting data about some part of the world and using it to model the entire world or a much bigger part of the world without needing to show every data point to describe the world. And someone put a DM to me, could this be used for COVID? Could this technique be used for COVID mitigation? If the example is sampling and population level statistics, absolutely. This whole idea of confidence intervals, of null hypothesis significance testing, of sampling from the population underlies all of science, underlies certainly medical science. The idea of collecting data about a sample, about some group of people that you have access to, in order to make claims about a much broader population. So it's the reason that a hospital like, I don't know, one of the ones that put out a lot of data during the pandemic was Johns Hopkins University Hospital in Baltimore in the United States. The reason Johns Hopkins University Hospital can put out data about COVID at a population level is because they can get data at the sample level and use statistics to make broader claims about the population. This is true across sciences. This is kind of one of the major points of using statistics, that we can use samples to talk about the broader population without having to get data from literally every single person in the world. That wraps up my quick review of why we even bother with statistics, why we are doing this in the first place. Remembering my scientific method diagram for last week, my wheel, we're in the process of exploring a hypothesis by collecting data, analyzing that data, and using it to build a statistical model about the world, then assessing how good or bad that model is. In other words, we run a study, not just to know something about our study, not just to know about the people who we sampled, but to know something about the broader world. In order to do that, we have to use data from our study, assess how well our hypothesis about the world might correspond to the data from the rest of the actual world. The tools of means and standard deviations are the building blocks we use to do this with all of our statistical tests. They give us things like confidence intervals that let us make these predictions of how confident we are in our hypotheses. The rest of the lectures from this point on, from the next several weeks, will explore different types of hypotheses that we can use statistics to test and how to assess whether or not the data that we collect fits the model that our hypothesis would suggest. We use these tools to decide whether or not the model that we're building of the world, or a hypothesis, describes our data by minimizing error, minimizing how far everyone was from the trend we're talking about. And we explore the differences between what the prior model predicts. So that might be a hypothesis we already have, or it might be just a null hypothesis. It might be saying that there is no relationship. Now we're building new models that say, here's what the relationship actually is. We're testing how well our new model explains the world as compared to the old model or the null model. Someone said, how do we define or pick a sample? It might have different means for different samples. Yeah, that's part of what this illustration gets at, that each sample will have a different mean. That's why if we had this sample, for instance, the one where their mean was 1, where the actual population mean was 3, that means our sample mean was not the same as the population mean for our variable. But because we know our sample mean will be somewhere on this distribution, it might be at the low end, it might be at the high end, we can at least draw an interval of all the possible values for the population mean, or all of the values within 95% certainty. Someone else asked, how do we determine the population mean to decide standard error? So standard error is, there's the mathematical equation in the book, but I'll tell you it now. I didn't throw it in a slide because I was hoping to not have to introduce formulas, because formulas scare people, but I should have had a bonus slide just in case it got asked. Standard error is actually estimated by taking our standard deviation and dividing it by the square root of the size of our sample. So the bigger our sample is, the bigger that square root still is, and the bigger our sample is, the less we have to adjust our, or the smaller, the tighter that window is. If we have a relatively small sample, that bottom number is really tiny. That means we're dividing whatever our standard deviation was by some really tiny number, and we're getting some really big number. We're getting some really wide standard error. The bigger our sample is, the tighter that standard error gets. And this is part of the mathematics behind this is in the textbook in our reading for today or for this week. But part of the idea is that we know statistically that this standard error, that the standard deviation of our sample means, the standard error for our population, must be lower than the standard deviation that we found for our sample. And the actual math proving that is in the book, but you can kind of take that one as gospel without needing to look at the equations. But we use standard deviation to estimate this standard error. We use that standard error to draw the size of our confidence interval. Yeah, someone said, could I explain confidence intervals again? So I use my standard deviation, and that lets me estimate my standard error. That lets me estimate how far the mean that I detected, the mean of my sample, is from the actual population mean. I know that my mean must be somewhere on this, this distribution of means, that if you took every single sample possible, like if everyone did a study with 20 people driving and texting or whatever, you know that all of the means that they found would be somewhere on this distribution of possible means. My mean is somewhere on that distribution also. I'm not sure where it is though, but I know the distances. I know how wide of the distance between my mean and the actual possible mean is, or the actual population mean is, because I know that even on the most extremes, since this follows a normal distribution, 99% of my data will be contained within 3 standard deviations. So if I'm 3 standard errors away from the mean, even if I had that extreme of a data set, even if my sample happened to be that far from the population mean, as long as I use a really wide confidence interval, as long as I use 3 standard errors, I would say there's a 99% chance that my sample mean is somewhere on this interval that includes my sample mean at the middle. Somewhere on that interval also is the population mean. Now, the more people I have in my sample, the tighter I can make those bars, the more specific I can make my guess about the population. But even with a small sample, I can take some guess about where 99% of the possible population means will fall. So yeah, this is to say, again, Andy Field did some kind of study for his textbook where he got a mean of 9 and he knows his own standard deviation. So he can build these intervals that say the standard error based on my standard deviation tells me that the population mean can only be this far away, or my sample mean can only be this far away from my population mean. So the actual mean for the population based on this study is estimated to be somewhere between these 2 values with 95% confidence. And again, if you're interested in like the math behind that, that is in the textbook, but we try not to make this too math heavy of a class. So you don't necessarily need to know the math. I won't ask you on the test or anything like, to explain why random variables are normally distributed. I might ask you the relationship between a standard deviation and a standard error, but I won't get too much more mathy than that. So if I didn't include the math in my slide, don't expect a formula to pop up later on. But if you're interested in it, they are definitely there to read. And these are the readings, chapters 1, 2, and 4. And yeah, before we get to a break, I just wanted to say that we should just keep oh, never mind. I guess I deleted what I wanted to say. Yeah, keep up with the readings anyway, because they will give you, they'll reinforce what I covered in the lecture, but they'll give you a lot more detail. They might make it click better than I did in my rapid fire version of this. So basically my lecture, the hope is that this gives you a basis that helps you read the textbook. The textbook will help the things that I said in the lecture click and give you more depth and more examples to help them click even more. So the textbook and the lectures are meant to be used together in harmony, not one or the other. So yeah, that's the reading. Make sure you actually get a chance to look at it, because that will really help a lot of these concepts sink in. But anyway, it is 3:03 by my clock. So we'll take a 10-minute break. We'll get back here at 3:13. And we're going to be using a new R file. So you probably found that on Brightspace, but we're going to be using the same driving.csv data set. And we're going to basically, it's really baby's first code. We're not going to try to do much more beyond what we did last week. So I'm going to slowly go through the first few things again. And if we're all on the same page, then we'll start looking at histograms and box plots. But if we're not, if there's trouble and we need some troubleshooting, then we can completely just do it all over again like last week. We can do it completely slowly and take our time with it, that we're not in a rush. Yeah, maybe baby's first programming is hard, but like, baby's first words are hard. Baby's first steps are hard. Like baby falls down and pronounces words wrong. Baby doesn't get it right the first time either. So baby's first code is not meant to be code that you can do perfectly the first time. It's meant to be code that you can make mistakes, learn from, and eventually master. So that's all I mean by babies first. I'm not trying to put babies down or trying to put babies over, right? I'm not trying to say that they're masters of this either. But anyway, I'll see you in 10 minutes at All right, hello, welcome back. I cut the break maybe a minute early. Maybe I only gave you a 9-minute break instead of a full 10 because I ended up talking a minute into the break. So sorry about that, but we definitely will have our foot off the gas pedal for today's practical. A lot of the code, almost all of it, except for like the very last line, is identical to last week. Just 1 hour of teaching and I'm losing my voice. I'm getting weak. Let me mute before I go. All right, here we go. So like I said, I'm always going to put these comments in, these hashtagged notes in my R files that help tell you what's going on. As you can see, I put some more spaces in this time in case you had some problems with the soft line wrapping, that thing where you go up into the code section and do the soft wrap long line. So now the lines split up on their own a little bit. Hopefully they don't split up too annoying of a way for you, but hopefully you should be able to see the notes, but also the code. And we'll see if our setting working directory, like the beginning of last week, goes well or goes poorly. So this week I did one little change to how I'm setting my working directory. So instead of doing the long format of like / and like the entire drive name, now I'm just doing this tilde and then R QDA 2022. So this is my root directory. So for my computer, that's for Justin's computer, that's documents, but for your own device, that might be some other folder. But if your QDA folder or your R folder or whatever happens to be in your root folder, then that might be a quicker way to set your working directory, or you might want to set it the same exact way you did last week if that were. So I already met with someone who wasn't able to set a working directory with the long format, but was able to set it this way. One other tip I have that I discovered in an office hour, that if you're able to set your working directory in your global options, but you weren't able to set it in code, you weren't able to use this set working directory command, you can just come into your options and copy it from here, as long as you found it over here. So if you copy it there and then paste it inside the quotes. For me, it's going to be the exact same thing inside the quotes, but for you, it might be a little different if you were having any trouble. So I set my working directory. I already am at my working directory, but now I go to working directory down here. I use that little more and the gear. Now it looks like our studio is looking in the correct place for my files that I need. So for my driving.csv file, but also my week 3 1.r script file. So again, there are some descriptions of how CSVs work, slightly different descriptions, but generally it says the exact same thing. But the first thing we want to do when we get started with a data set is just load that data set into our environment. So I run this line of code. For me, I'm hitting Control Enter. If you're on a Mac, it's Command Enter. You can also just click, but I hit Command Enter or Control Enter on that line. That tells R to run that line of code. It's also just going to throw all of the comments above that in there, but R just skips any comment. So anything that starts with that hashtag, it's ignoring anyway. So it doesn't even do anything for all those. Then it runs that driving equals read.csv. And you might have noticed in your global environment, hopefully when you ran that, driving popped in there. You have 17 observations, so 17 participants of 4 variables. So 4 columns of data, 17 rows of data. And just like last week, that worked for you if you got your driving into your global environment. Then we can start looking at that data. So again, before I even do like a histogram or a scatter plot or a box plot or anything like that, I always look at the head and the tail. So I ran my head and tail commands. And again, you can run them by clicking run up here. You can hit Control Enter, Command Enter. You can highlight what you want to run and either click on run or click Control Enter. Any of these methods all work to run, whatever feels comfortable for you. But yeah, I normally look at my data frame in terms of the head and the tail. So I look at the first few rows and the last few rows, and I see what my column names are. So I say that my first column's ID number, my second column is condition, so either texting or no texting. My third column is reaction time, and my fourth column is driving score on a scale of 1 to 10. And again, this is just like fake data. So it could mean anything. I interpreted it, or I thought of it as meaning that reaction time is how long after the light turned green did the driver notice and press down on the gas. And score was also a research assistant was here rating everyone's driving score on a scale of 1 to 10, watching and noting down their driving score subjectively. So I have these 4 columns of data, and I have 17 rows. So I know that I have 17 rows because my last row in the tail is labeled as row 17. And I see that, yeah, my condition can either be texting or no texting. That's a categorical variable with like text as the data type. My reaction time looks like a continuous variable that has numbers in the thousands, so it's probably milliseconds. And my score variable has numbers from 1 to 10. That fits with my understanding of what this data is. That's already a good sign. That would be bad if I didn't recognize a column in my data or something else went weird. That would tell me that I probably need to re-import the CSV file that I did something wrong, or I saved it badly or something, but it looks good, so I can carry on. I might want to check out that entire data set just to see, maybe I missed the people in the middle, so I'm not sure if there was a third condition. But when I look at the entire data set by running just the name of the variable or just the name of the data frame, just driving, now I have all 17 rows printed here. I have all of their data. And I can see that, yeah, all these participant numbers are there. So I didn't lose any participants. I can see that there's just 2 conditions. There's just texting and no texting. And I can get a look at what everyone's numbers are. Also, I made this note last week, but if you want to view them in a new tab, if you don't want them just printed in your console because it's kind of ugly down there, and you would rather be able to like sort columns like an Excel spreadsheet, then you can run view driving or view whatever your data frame name is with a capital V. That's important. R does care about whether your letters are capital or lowercase. And now you have the same that same data, but instead of printed line by line, it's now sortable. You can sort it whatever way you want. You can sort everyone by their reaction time. You can sort everyone by their score. And that's just another handy way to start looking at your data to see if there were any problems or anyone that stood out or any point that you wanted to investigate further. So, and this should all still be review, but please put a message in chat if anything's not working for you, if you're not sure why I'm doing something or not sure why I'm using a certain word or anything like that. Please just let us know. So next up is just looking at an individual variable. And a lot of times when we're running our statistical tests, we might be running them on a single variable or running them on just 1 or 2 variables. So we don't need to look at everything. So we might just need to look at one thing. And first, let's just look at ID numbers. So like I said, we want to make sure that our head and our tail or just our visual inspection that we didn't miss anyone. We want to see that all of those ID numbers are there. So to look at just one variable, you can put the $sign in. So you can do driving $sign ID, and that gives you every ID number. So it prints that 1 to say that this is the first one here. Someone asked last week, why does it print a number there? So if I made my window really skinny and then did driving $sign ID, it has to print on multiple lines. So instead of making me look at my screen and go 1, 2, 3, it actually just tells me that here's your first one, here's your 10th one. It'll just print out in brackets what number the nearest value was. That way, yeah, you don't have to count how many you had. It helps you count. We could do this with any of our columns, and you'll notice as you type, if you do driving $sign, R actually tries to help you out. It's pretty cool. It's an RStudio feature. R, if you just used R without using RStudio, you wouldn't get things like this. Depends how interesting that is to you, I guess, but I'm interested in it. I hate typing things out. So RStudio is offering which one of these I wanted to use. So I wanted to use, maybe I want to see all of the reaction times. So I click on that and I can run that. I see driving reaction times all in one row, or maybe I want to see score. So I don't need to click. Now you can't see where my hands are, but I'm only using my keyboard now. I can go down and pick which one I want with my arrow keys and hit enter on it, and that'll type right in there for me. So I can get all of that. Someone said, can we print 2 columns simultaneously, like ID and score? Sure, we could do that if we wanted to. So if we wanted all the IDs and all the scores, we could do with a semicolon, do driving $ID, driving $score, and oh, it didn't like that because I didn't capitalize the S in score. I already warned you that R is really particular about capital letters. It's particular about like commas and quotation marks and all of these things. I would say at least 75% of code errors you'll run into, like this null that I just got, is because of either capitalization or a missing comma or a missing decimal point or something, or a missing parenthesis, I mean. So always look for those kind of things first before you think that you messed something up badly. So let me fix that. So now, yeah, I print 2 columns simultaneously by putting that semicolon in. So I got my first output is all of my IDs. My second output is all my scores. That's just one example. You could put any other kind of combination of commands all on the same line. Yes, R is case sensitive. R cares a lot about mistakes, and it's not very good at telling you what your mistake was. So there, notice when I typed in driving $score, it told me nothing at all. It just said null because I didn't have that capitalized. Let's see if I had them on, if I had its own row and didn't have score capitalized. It just tells me null. It doesn't give me any further information to help me diagnose my error. So that's why we say in our email policy, try to diagnose it on your own and like tell us what steps you took, because the first step I'm going to take is checking spelling. And it's going to be pretty rude if you said you were working on this issue for hours and the first thing I write back is like, oh, did you check your spelling? It's like when you call like IT support and they're like, oh, did you try turning it off? And you're like, yes, I tried turning it off. Yes, I checked my spelling. It's the reason I ask for all that documentation or all of the evidence of what you've tried so far is because I don't want people to get pissed off at me when I suggest simple things like, did you make sure the letters are capitalized? But that's normally what your issue is going to be anyway. So since we can look at individual columns, that means we can get statistics for individual columns. We can get descriptive statistics. And I'm even going to add standard deviation down here. I'm going to do driving $reaction time. So I can get my mean, my max, my min, my median, my interquartile range, my standard deviation. And if I'm reporting stats about this particular variable, if reaction time was one of my variables of interest, if it was part of my hypothesis, then I would want to describe that variable to my readers. So I would print, or I would put into like a report all of my descriptive statistics that I thought might be interesting, which at bare minimum should include mean and standard deviation. But I think it's also nice to include things like min and max, and to include maybe a median to see if your median and your mean were close to each other. I think it's always good to include all of those when you're reporting descriptive statistics, but at an absolute bare minimum, please at least tell your reader what the mean and standard deviation is for any data column that's part of a hypothesis, because those are the 2 stats that, as I said in the lecture, like you get so much information out of those that without them, your reader's really left guessing. I said, wouldn't it be better if we use a bar chart instead of a histogram? So bar charts and histograms are pretty well related. The big difference is that histograms, the bars touch each other, and that's actually informative. When we get to the bottom of this file, we'll talk more about histograms, but histograms, the bars touching each other matters, that data is continuous, that there's no gaps in the buckets, there's no gaps in the steps between your histogram, that it's not that a data point could have fallen between bars, that the feature of the bars being right next to each other is part of the histogram's visualization. It's an important part. That said, a histogram is a type of bar chart. It's a bar chart in which the bars touch each other. Because the histogram is used to talk about frequencies of how many times each value occurred, then because histograms used that way, people expect if you're talking about frequencies that you're using a bar chart, or that you're using a histogram. So if I see a histogram, I'm thinking you're telling me about frequencies. If you're telling me about frequencies, I'm expecting you to use a histogram. That's not just me, that's like anyone reading scientific or mathematical visualizations. So bar charts are used in other times. We will use bar charts later in the year for visualizing differences between means. But for visualizing your frequencies, you definitely want to use a histogram in specific. Someone said, can RStudio visualize and export histograms? Oh, can it? If I'm pleasantly surprised that we're not seeing so many errors. I didn't know, or so many, I don't want to say errors, so many issues with code that it's not your fault that if R is not working for you because of like, you know, administrative settings or something. But because there's so little troubleshooting, we will get to this histogram section. And that's where I'll show you not only how to make the histogram, but also how to tidy it up a little bit, how to make it look a little bit nicer or different, and also how to export that image or how to save that image. So that's all of our descriptive statistics. I will give you some code in a week or two to get all of these done at the same time if you just want all of these descriptives kind of run at once. But it is fine to say to run them all on one line or to do summary of driving $ reaction time to get some of these values. So if you don't feel like typing it all out, but you want to put your mean and your median in some report, you can use that summary. I write a custom little piece of code later on that I'll give you that lets you run summaries that also include your SD. That way you can just run that one line and get everything that I would normally expect in your descriptive statistics. Someone said maybe Python is better than R. Python's better than R for some things. It's better if you're doing back-end web development, for instance. But that saying Python is better than R is like saying a hammer is better than a screwdriver. Like, yeah, a hammer is better than a screwdriver at driving a nail into the wall, but a screwdriver is better at driving a screw. R is better than Python at dealing with tabular data and doing statistics, but Python's better than R at dealing with non-tabular data. So dealing with like images as data or words as data. It's better for like, yeah, back-end web development. It's probably better at object-oriented programming, though you can do both. You can do each and either. Either can be used for machine learning, either can be used for tabular data, for data visualization. So it's not that one is better than the other, it's that they're different tools that you use for different jobs. People say that every year, and I'm always like, again, like, yeah, if you really want to drive your hammers in with the back of a screwdriver, or if you want to drive your nails in with the back of a screwdriver, I've been there. Like if I can't find a hammer, but I have a screwdriver, I will use the wrong tool for the job sometimes. But it's nicer to use the best tool for the job. How do you know what units are in the console? It's always the smallest type of unit possible that the data aligns with. You don't know what the units are in the console because you actually don't know what the units are in your CSV file. So I'll actually open my CSV file. I won't bother opening it. You could open it yourself in Excel or in Google Sheets, and you'll see that there's no unit there. You don't know what the unit is. It's hopefully, like if you're the person collecting the data, you know what unit you were collecting that data in. Or if somebody gave you that data set, they'll tell you, they'll either give you a description of your data set, or they'll tell you in the variable name, like reaction time, and then in parentheses, milliseconds. But R doesn't know what the unit is because your CSV doesn't have any information on what the unit is. And that's how it goes in real life, to be honest. Like when I collect data for my own experiments, I would know what the unit is for some of my variables, but they're not reflected anywhere in my actual CSV, in my actual spreadsheet. Likewise, if I get data from someone else to do some statistics on, like if one of my colleagues is like, Justin, you're the guy that knows how to do R stuff, will you run some stats for me? They'll normally send me like a description of what each data column means, but they won't have that anywhere reflected in their in the actual data. But yeah, since my mean for reaction time was 3,186, I'm assuming that's milliseconds. It's 3.186 milliseconds. Standard deviation, which the reason I like standard deviation, the reason we really like that more than variance, is it is in the same units as your actual data. So if my data is if my reaction time data otherwise was in milliseconds, my standard deviation is also in milliseconds. Yeah. So my standard deviation for reaction time, 987 milliseconds or 0.987 seconds. But that's a really good question. So that's that's your summary statistics, your descriptive statistics. Those should probably go with every kind of data that you are testing, everything that we assign in this class. You'll always want to tell us what the descriptive statistics are. You'll always want to include them in a report, like in a table, like for here's all my variables of interest, here's their means, here's their medians, here's their standard deviations, their min, their max. But now let's also get into a little bit of visualization. That I think we can cover histograms. We might even start doing some box plots too. So let's look at a histogram of driving scores. Now, driving scores, as I said, was the scale of 1 to 10 arbitrary scores that you could either, you couldn't get like a 3.5. This was someone rating you on a scale of 1 to 10, where there was only whole numbers. So when I just tell R to make a histogram of scores, it does a pretty good job with it. It knows exactly where to like break these down, but it theoretically could have broke these down anywhere, right? It could have said like anywhere between a 4.5 and a 5.5 is in this bar, which would be weird. Like why would R do that when we have whole numbers? R sees that we have a bunch of whole numbers and does a good job of saying like, here's a bar for 1s, for 2s, 3s, 4s, 5s, 6s, 7s, 8s. So we have a pretty nice looking histogram for driving scores for that column. If I wanted to make a histogram of reaction times, you'll quickly see that R doesn't play so nice. If I do reaction times, it's not bad. It's somewhat descriptive, but I think it could be a little nicer looking. That R picked 1,500 as the minimum here, it picked 5,000 as the maximum. But those are arbitrary. And in fact, we know that reaction time has an absolute zero of 0. You could have reacted in 0 milliseconds, right? It's an interval, it's a ratio scale variable. So we actually should probably look all the way from 0 to whatever our max was, or maybe a little higher. So we can add things to the histogram command that we don't just have to have the column name. We can add other things we want, like maybe a title, main title, histogram of, I said score, whoops, reaction time. Gotcha. We can add other information to the histogram, like an x-axis label. So again, I said score, but I actually want to do reaction time. So I'll do histogram of reaction time. You know what? Let's leave it at score because of how I made these breaks. Then we'll do a separate one for reaction time. Sorry about the confusion. So I'll copy that there and put it here. So one issue with my histogram for score, by the way, was it doesn't go to absolute 0. That we don't have. It doesn't go from 0 to 10. It doesn't go all the way to 10 either. So it doesn't really represent what our possible maximum was. And we want it to represent our full range of possible values. We want to see whether our values were kind of tightly constrained in the middle, even though they could have been lower or higher, or if we did have a spread across our possible values. So we'll leave this first histogram as score, and then I'm going to make a separate one for reaction time. So yeah, I'm adding histogram of score as a main title. So I just put comma main equals, and then in quotes, the name of the main title. X lab, so X label equals, and then in quotes, score. You'll notice here I use double quotations. Here I use single quotations. Doesn't matter which one you use. I don't know why I switched between them. I'm a weird programmer in that way. It means nothing. So I could have done, I could have and probably should have just done double quotes around any time I wanted quotes, but you can use a single quote and a single quote, or a double quote and a double quote. They do the exact same thing, and I'm bad about switching between them arbitrarily. But the final thing I want to adjust here is the breaks for my histogram. I want to tell R how many of these different buckets, how many different spaces for bars it should draw. So I want it to have a bar for a score of 0, and I want it to have a bar for a score of 10, and I want it to have a bar, or a bucket for every other possible value there. So when I do it that way, I get a slightly different histogram. So notice before it said histogram of driving $ score. This said driving $ score. And I didn't have my 0 and I didn't have my 10. Now with my new histogram, I do have a spot for 0. So I have a spot, no one got a 0, but someone got a 1, someone got a 2, et cetera, 7s, 8s, 9s, and then no one got a 10. But now I can see more clearly how my data took up the entire space of possible values. So here I had people bunched up between, I had the space for people who got a 1 on their driving score just bunched up against this left end, that it made it seem like there was nowhere else to go. Yeah, sorry, I'm doing a poor job of explaining this. I can see questions coming in already. The issue with this first histogram is I didn't separate out, for example, that you could get higher than a 9. So here, the last thing that R drew when I didn't give any specifications of how wide to make this histogram was 8. So this is 8, this is 9s, but it doesn't have a spot for 10s. Even though no one scored a 10, 10 was a possible value. So I want that represented with on my histogram. I want to see that the 10s are there. When I ran the same line, it didn't resemble your third one. That also happens. So R definitely will draw this histogram however it sees best. And I think one thing it takes into account is how big your screen is, so how much space you have for the bar. So if I make it really wide, I wonder if I get a different looking histogram. So now it's really wide. No. Well, if you don't specify anything, R is going to try to specify things for you. If you specify things, R will make it whatever you specified. Why does my y-axis have decimals? I think R, for some reason, thinks you can get half of a person here, even though you can't. I could specify that too. So I could say y. Let me check the help command to see what I can put into hist. So that if I go into the help tab, I can check what I can include in hist. So I can include things like x limit, y limit. So I might include things like my y limit. I could specify that myself. I could clarify this scale for y. But I don't really care that it has that decimal point because it didn't use them. I could write in an extra line here that's like y lim equals, and then put everything, put all of the values that I want in there, but I don't really want to bother with that. One other issue I noticed about this histogram that I didn't like, that I do like about my new histogram, this one's grouping 1s and 2s together. So notice one person got a 1, and then 1, 2, 3 people got 2s. So it's putting all 4 of those from 0 to 2 all in one bar. That's not telling me a lot. That's not telling me all the possible scores. My histogram breaks things down so each different possible value has a bar. So now 1s are on their own. We see one person got a 1, 3 people got a 2. R is no longer trying to group them together because I told it how to break things. And that's what these breaks, that's what this breaks function is. So breaks equals, and then C just means concatenate. You don't need to know what the C means, but whenever you're putting more than one thing in parentheses for R, you put a C before the parentheses just to tell it this set of parentheses is going to have multiple things in it. So my breaks are at 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So there's a line gets drawn, a vertical line gets drawn at 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. You don't necessarily have a bar at each space, but it means I actually want to separate them out, that I don't want them grouped together. Now that breaking is arbitrary. I could make my breaks anything I want that are inside of my range. So I could have said breaks at 0, 5, and 10. And I would get a histogram that looks like this. I would just get a histogram with a line at 0, a line at 5, and a line at 10. And this stinks. I don't want this at all, right? Why would I want to just know? Maybe I would want to know how many people got above a 5 and how many people got below a 5. That could be interesting to me. Sorry, someone asked, how are the two histograms different when the command is similar? So that command hasn't been used yet. I'm comparing this histogram of driving score to this histogram of driving score with all of these specifications. So the differences are the titles, but also the breaks. And now I'm comparing this as well. So if I drew just breaks at 0, 5, and 10, that looks terrible because I don't want to just know how many people got below a 5 and how many people got above a 5. I want to know how many people got each individual possible score. So I specify all of my breaks in that C, and now I get a much better looking histogram or a much more informative histogram anyway. The default breaks are determined by magic. An evil genie who works for R decides them. I have no idea how R picks its breaks, and it picks them pretty bad for a lot of data. That's why when you're making a histogram, I would say you should probably always choose your breaks yourself, define them yourself, because R, even as people were saying here, their version of a histogram looked different than what my R generated when I didn't specify breaks. That's bad news, right? If R is choosing the breaks so arbitrarily that we're running the same code and you're getting different breaks than me. So always specifying the breaks that you want to see makes it so the histogram looks more like you want it to look. So let's do the same sort of histogram, but for reaction time, and we'll do this together. So it might go badly wrong. Someone said, Excel is better than R. Again, yeah, my water bottle is better than my coffee cup, unless I want coffee. You know, like it's all depends on what you're using it for. That Excel is better than R for looking at your data, but R is going to be a lot better than Excel for testing hypotheses about it. You can do both and both. I could drink my water out of a coffee cup every day, but I would have to refill it more. I have a pretty big water bottle. Or I could drink coffee out of this all the time, but this is made of plastic, so I'm probably going to drink a lot of like molten plastic over time. Oh, all of you must be pretty special. You got me there. Yeah, I fell for it. Someone said, yeah, everyone's getting the same except for me. Yeah, it's probably because I have like messed up stuff on my R. I probably haven't updated stuff in a long time. I probably have like lots of packages interfering with one another. I'm glad everyone else's is looking the same and mine's looking bad. Also, someone said, how can we define the y-axis groupings? You can do that using the y-axis, the y limit command in here, the y limit argument. I don't bother with that because I just kind of want to know an overview of how many were in each group. I don't need to know the exact amount of people in each bucket, in each break, but that's fine. So let's see what the reaction time histogram is going to look like. So I'm going to take that reaction time, histogram of reaction time, X label will be reaction time. And I know from earlier, my min and my max for reaction time were 1825 and 4912. So that gives us an idea of where to set our breaks, except for the fact that reaction time is ratio data. So I actually want my first break at 0, but I know I want to go all the way up to 5,000. So I might set my breaks every 500, say. So I might do 0, 500, 1,000, 1,500. I know how to count. 2,000, 2,500, 3,000. There are ways to do this simpler, but I'm doing it in the most aggravating way, so you know what exactly is happening under the hood here. And 5,000. So if I make that histogram, now I can see the distribution of all of my possible reaction times. It goes all the way down to 100 possibly, but it actually groups more like that. So now I can see all of my reaction times as well. I could have chose different breaks. So I could have only chose each 1,000 as a break. So I'll get rid of all of the 500s here and we'll see how different that looks. That's a lot less informative because I chose less breaks. That means more are getting crammed into each bucket. I'm combining like neighboring groups together. So this is a little more informative because I chose a smaller amount of breaks. I could have chosen breaks every like 25 milliseconds. That probably wouldn't be so informative either because there wouldn't be like multiples in any given bucket. Someone said, is it possible to get a combined histogram of score and reaction time? Unfortunately, for variables like that, it is not, because those two variables have different axes. Those two variables have different units. So they have reaction time is in milliseconds, score is on this 1 to 10 scale. So there wouldn't be an easy way. There would be some ways to have two different y variable axes, but you wouldn't want to bother doing that for your histograms. Yeah, you're absolutely right to say this is probably not normally distributed data. It looks like I have data that does not come from a normally distributed population. And you might have a guess as to why this data isn't normally distributed. As I try to remember how to do sequences. So there is a way to not have to write all the numbers. It's seq 0, 5,500. Is that right? Yes. Oh, he's a master of programming. So if I wanted to not write all of this data, and if you have any guesses about why this data might not be normal, throw them in chat. So if I didn't want to write all of that out, I could write the sequence command. So seq is sequence from 0, comma, to 5,000, comma, every 500. And, well, it worked because it drew the same histogram. So if I run that command fresh, it does the exact same thing as if I wrote it out longhand. Now, I kind of prefer to write it out longhand when I show it, because I think that helps you know exactly what's happening under the hood. But I could write like, this is the same thing as the previous. So instead of writing out every single break, nope, this is the same thing as this one. Where is it? 500,000. Yeah, this is the same as this one. Oh my God, he's lost his touch. He was so good at programming just moments ago. Yeah, now this one where I break every 500 is the same thing as using this sequence command. I didn't see any guesses. The reason that this data is probably not normally distributed is, so that's a description. So there's no appropriate bell curve. That's how I know it's not normally distributed. But the cause for that lack of normalcy is because there's two different conditions. So I'm not sampling from the same population. I'm sampling in one case from a population of drivers who are texting, and in the other case from the population of drivers who are not texting. So when I combine their data, when I look at it all together, I don't get a normal distribution because I have two different populations. In future lectures, like next week or possibly the following week, we're going to start looking at individual conditions. So maybe if we looked at just reaction times just for texters, we would see a normal distribution. If we looked at reaction times just for non-texters, we might see a normal distribution. That'll be the focus of the following couple of weeks, of trying to figure out if we have different populations that we're sampling from. Someone said, can we filter the histogram for a specific condition? Yes, we'll get into that in future weeks of separating out individual conditions as their own data frames and using, just looking at reaction times of texters and getting a histogram for that. But that is future scope. Hopefully today wasn't too horrible and confusing, but please send me your questions in email or in whatever other method, Brightspace, or meet for office hours if you need to. And thanks for sticking around. Thanks for being here for the practical. I've made it a case to try to get you guys out here not too far over the time limit, especially since it's a later class. I'm glad today's class was helpful. I'm glad this worked a little bit better for you. Yeah, we'll try to keep things at this, we won't do so much repeating like this week, but we will try to keep things at a relatively slow pace in the practicals. So you'll gain something new each class, but we'll try not to make it feel too rushed because it is new. It is tough to learn all this coding while you're also learning the statistics. So I'll see you next week. I was going to say I'll see you Tuesday if you're in UXD, but I will not see you Tuesday. I will see you Thursday for QDA.